All right, here we go. Solving number 2 on lesson 9 for Thevenin equivalent circuit. So we know, even before we start writing things down, the Thevenin equivalent circuit will look like this, right? And here is our load. This is a variable. That's what the arrow means, is that we can adjust it. In the physical lab, we have these little knobs that we turn to adjust the resistance. And in the final circuit, we will have an R Thevenin and an E Thevenin. And so a couple ways to just think about what does it mean to say a Thevenin equivalent circuit. So far, if we had resistors, say these were all in a series, and I said that you wanted to put them in a box and say that all 3 of these together make some equivalent resistance that can be modeled like that, right? That if I want to take that same idea and I put everything inside of this green box between A and B, and then I put it in this green box, it's an equivalent. From the perspective of this variable load resistor, from this guy right here to this point right here, he can't tell the difference. As a resistor, imagine you're the resistor sitting inside the wire and you see electrons flowing at you. You can't tell what's producing the electrons. All you know is they're coming at you at a certain rate, and across you is some voltage drop, A to B. You don't know what it is that's creating that. It might be one voltage source with one resistor, which is a Thevenin equivalent, or it could be something more complicated, which is actually even why I use things like Hamilton or Leibniz. I'll tell my students, when I see Thevenin, what it means is I can do it, right? I can overcome, I can win the American Revolution or fight at the barricade. And the reason why is because no matter how complicated of a circuit it is, it can come down to some easy circuit that looks like this, a tiny little baby series circuit, right? So that's the idea of a Thevenin equivalent. Now, how do we actually solve for it? There's a couple ways that you can analyze it by looking at it, but I recommend often redrawing it, right? So if I was looking for the E Thevenin circuit, you don't have to redraw this one, because you can also just put your thumb over it, over the load resistor whenever we remove it. But the reason I find it helpful to redraw is that whenever I remove that load, right, I've removed the load resistor, I can now see that this 15 ohm resistor has nothing flowing through it. Whereas if you don't redraw it, you have to remember that this 15 ohm resistor is effectively dead. It just acts like a wire. There's no current flowing through it. So if I was labeling nodes, it is a part of that node now. Nothing flows through it. So we don't include it when we look for the voltage drop across node A to node B, right? The open node voltage from there. The fastest way to do this one would be with VDR. Right, and VDR says Vx is equal to VEQ, Rx over REQ, the R equivalent. Well, what is the voltage being shared? It's 10 volts. Remember, we said VDR is only for series elements. So whenever I'm doing this right now, 6 and 9 are in series. They exclusively share the node A between them, right? And so those together, I'm looking for across A to B, which is the 9 ohm. The R equivalent is 6 plus 9, and that comes out to 6 volts. So that's my E Thevenin equals 6 volts. What is my R Thevenin? I'll draw it over here. Here's my R Thevenin circuit. This one, I definitely recommend redrawing. If you just put your thumb over the load whenever you're doing the E Thevenin, that's fine. This one, it's almost always worth redrawing, because when I zero the source and I'm making it really thick, to remind you, that's just a wire. Here's 9, right? I've replaced that voltage source with a wire. 0 volts, there's no voltage drop across a wire, right? The voltage is constant through it. So 0 volts, 0 voltage potential difference is a wire. So if I'm labeling nodes now, I'm looking for R total from node A to node B. And there's one more node right there. So what do I see is that 6 is paralleled with 9, and that gets added to the 15 right here. And that is my R Thevenin. All of those together makes, I got 18.6 ohms. So R Thevenin is 18.6 ohms. The last step, it says determine ILD. when our load equals 2.5. So I'm looking at I total in the circuit, right? There's the current I total. So I total in this circuit is V total divided by R total. And the reason I'm doing I total is because I don't know the voltage drop across our load. I could get it with a voltage divider rule, or I could just say I total is equal to I load because it's a series circuit. The same current flowing throughout. I total is I load. So V total in this case, 6 volts. R total is 18.6 plus 2.5. And that comes out to 284 milliamps. For box and answers, it says the Thevenin equivalent circuit. This in green is the answer, and this 284. All right, those are the two parts that we were asked for.